So first and foremost, we're gonna show a demo of the software which is online, and then show some value cases at the end of the presentation. When you come here, you type WellTest Nordisk altogether.com, and you get to this page where it's written well testing analysis uncertainty, because we analyze the uncertainty on the well test results. And as we go down, you have a description of the MonteCarloFlow software, and the first thing you can notice are 3 links. So link number 1 is actually referring to the main study that backs this software, and it's called Evaluation of Confidence Intervals in Well Test Interpretation Results. This was published in 2007-8, and it was written by me and several other colleagues, Alain Beau, Tim Whittle, Alain Greengarten. So this dates from 2007, 2008, but note that there are about 20 plus references that backs this software, and I won't show all of them, but you can say that these 20 publications are the key ones. They're in fact the pillar of this tool, and studies that preceded this tool go way before 2007. So to go to a short list in link 2, we have the different milestones and work, theoretical work and practical work that preceded this software. The first tool started in the first publications were made in the 70s by Remy et al. And then you had computer-aided well test analysis in the SPE papers by Greengarten et al. In 86. And then uncertainty in well test interpretation, I would say first comprehensive attempt made in 94. And errors in input data and the effect of well test interpretation results by Spivey and Purcell in 98. So you see these studies, they started in the 70s, they restarted in the mid-90s, and it continued with Alain Beau thesis, which preceded mine at Imperial College, and then my study in 2007. This is just to give you some background on the different research that preceded this software. So let's move to the input data. If one goes to how our software functions, there are different set of data, and it's important to discriminate between them. The static data are those called basic data at the left hand side. So these include matrix porosity, reservoir thickness, wellbore radius, the volume factor, oil viscosity, and if we treat the oil case, the total compressibility and the production rate. The total compressibility and the production rate. These are preliminary to any well test software, and they will be preliminary input to our software. The second set are the match parameter hereby, and this match parameter, there are some assumptions that come with it. The model selected has to be right, and these parameters are always consistent with the static data on the left, and these match results, they will depend on the quality of the match. So among them you can see typical dimensionless match parameters like PM, TM, CD exponential to S, etc. and so forth. You also see dimensionless match parameters that are linked to the geometry of the well, like HWD, ZWD, and some specific to double porosity, for instance, or double permeability. So as I mentioned, the interaction are accounted for. This set here and this set here that you will both input in our software, they are consistent. These one are original static data that you input, and these come from the interpretation that you perform. So you have to select the model, and we assume that you have selected the right model. Once you select the model, you will have a sublist of this match to choose from. All these results are computed in the Monte Carlo algorithm, and you get the uncertainty of interpretation results on our final results. This can be KH, the conductivity, the skin, the wellbore storage, the distance to a fault, or the permeability. We can show some examples of performed match. Here you have, as mentioned, the CS, so wellbore storage, permeability, conductivity, skin, vertical permeability, for instance, and all these results, these are the typical results on which we will have our uncertainty analysis run. You can see that the user has defined a model, so he mentioned the use of Packer, partial penetration, late time behavior infinitely acting, and in this case a constant compressibility. This is another case of a successful match, and hopefully the proper model chosen, and you get the same sequence of results. Note here that the model is a radial homogeneous behavior, parallel faults, etc. and so forth. This is mostly to illustrate the CD exponential 2s match parameter, and for each of these lines you have a specific value of this match parameter, CD exponential 2s. So it shows you how it's computed and how it behaves depending on its value, so damaged well, non-damaged well, or acidized well. For those who have eventually forgotten a bit or need some refreshing about this notion. So if we come back, once we have selected all the right input in the Monte Carlo algorithm, there is a probability density function. In our case it's predefined, that will be selected for each and every input in the static data that you see here. Each and every input, in our case they are predefined, and the error range are also pre-selected, and they will define the mean, the high, and the low for each case. The selection and the reason why they are not user defined is because they are based on our previous research. Let us move to the actual software and see how it works. So we will get back to the main page, and you get on the upper right side 4 different cases: 2 cases for sandstone, 2 cases for carbonates, and each is distinguished by above bubble point or below bubble point. Above bubble point, below bubble point. So let's select the first one for the sake of it. It leads you to a page where you input your password to access the software. Then you click OK. It leads you to the page where the software is contained, and you define your parameters. What you can see here is at the top. The first half contains all the static data, and the second half contains all the match data. So it will run a probability density function generator using 10,000 trials, and that delivers a very tiny errors compared to the error we try to provide for the WellTest results. It provides the results as percentiles. So let's just put some dummy values to start with to show quickly how it operates. And click pressure above bubble point. PB stands for bubble point. And if we go down, we click on click me. It takes a bit of time to run. Actually, it's quite quick. And you get the results as percentiles. So you get your P90 for the conductivity KH, you get the median value P50, you get the P10, you get the mean KH or conductivity, and you get the standard deviation on your conductivity as well. And the same happens for permeability, for SW, the mechanical skin, not all the skin but the mechanical skin, for wellbore storage, for the distance to the fault, and you get a plot which shows your probability density function for KH and for K. So that's after we run the Monte Carlo simulation, and the level of complexity is a square number of the number of trials, but the simulator still runs pretty fast thanks for some coding choices and because it is server based. Now we will move to the value cases. So the value cases are examples where we can show that that this adds a lot of economic value. So for instance, we will start with exploration, then move to field development, and finish with operations. So this is an example. This is a telling example to see how an uncertain appraisal for oil and gas reserves can be narrowed to in order to make a decision. So the A plot, the B plot, let's start with the B plot, shows you a spread of the reserves, a spread of the reserves which is pretty large. So it shows you an area of interest in this place, but you still have a lot of area on the tails, and that creates an uncertainty, and it can make it for your management difficult to actually invest on such an opportunity. With our tool, we can narrow so much the uncertainty that we can get the A plot, where you don't have a lot of area in the tails, and you can be more confident on the value close to your mean, and that actually may make a case non-economical economical. So that's a big interest of using WellTest and also the uncertainty on WellTest useful. So you see the median value is promising, but the spread is too large in the B plot because the probabilities on the tail are too large. to deem this project economic because too risky. But once we refine our well-test uncertainty, we can move on to a case where we can deem this project economically viable. After using our tool, we can eventually get a narrowed estimate, which puts the probability closer to the mean and helps make the right decision. So that's one of the use, especially if you do a material balance evaluation at the beginning of a project in the exploration or appraisal phase, and it can definitely change the picture. Now, the second case is the case of field development. So in field development, first of all, knowing the uncertainty on your well test brings more value when you use your well test permeability to compensate for lack of data from the core and the logs. Also, quite often you are asked when you do field development as a reservoir or production engineer, the drilling engineer may ask you about info on drillability, and this is nowhere to be found, or sometimes you can extract it from the geology or from the static model or the dynamic model, but it is sometimes hard to compute. Another way is by providing the production index on a deviated or horizontal well. Sometimes it's hard to compute on your dynamic model, so you may be able to get the value from well testing. And refining the uncertainty on well testing make it even more important for the drilling engineer, because he wants to know the production index, because he wants to have certainty on the pressure prognosis. So as you may not know, the core uncertainty is usually 40%, while the well test uncertainty is only 15% on average. So that because of the averaging of the probabilities along the pay zone. And that brings value to our tool. Also, when you upscale, you need to keep consistency between core and logs and the well test actual flow, and this may reconcile both of them. So better upscaling means in the future better history matching, and we will actually move to that in the operational case. So this is a plot in when you work in operations of an attempt to history match a curve. So typically you have this red cross which represent the actual gas production data, and you have different attempts to match it. So you have a plot that matches it at the beginning but not the end, and the green plot that matches it at the end but not the beginning. So one can play on many values to try to match this. You can play on the bubble point, on the GOR versus depth, and still not be able to manage it. Actually, the key factor here is the relative permeability, how the oil moves versus the gas, and how the gas moves versus the oil, and that's what was found at the end of the day. So our tool intervenes at all the stages of the value chain and largely in operations. For example, for the production level, the productivity, the kinetics. In this case, the kinetics. And of course, having the rel perm right is important, but you will still multiply it to get the absolute permeability, and the magnitude of the permeability also come into account when you try to match this plot, and our uncertainty tool can help you refine this upscaling, this history matching, sorry. And therefore you will get not only the recovery factor but no better the ultimate recovery, and that's very key, because we don't only assess how much we recover, but the kinetics of how we recover these reserves. And that's what makes this history matching process more advanced. It also can come handy when you play with smart completions as well. So let's look at the added value in different sectors. In exploration, we saw that it's useful for NPV, reserves, and profit, for production, productivity, and cash flow. In field development, we saw that it can assist the upscaling process, the history matching process, add precision on the production index of different formation, and ensure added security, knowing drillability and the pressure window. In operation, it also helps for NPV, reserves, estimate and profit, and also a lot in history matching. To show you in a more dramatic manner how it plays, we can take an extreme case. It's an extreme case in its consequence, but not in its occurrence. If the DI is the error range, if DI is the distance to a fault and K is your permeability, the error of DI can range up to 30%. Let's take 30% as the extreme case, and K can range up to 15%. If we are in a specific type of closed reservoir, as I said, the consequence is reservoir dependent, but if we use a sealed fault block or another type of closed reservoir, the above can alter the reserve by as much as 50%. So you get a fake sense of control of your reserves when you run a conventional analysis of the uncertainties on your dynamic model. But when you forget to use our tool, this is by how much you can miss the plot. Therefore, running reserves appraisal without this tool should not be taken lightly, and uncertainty analysis run on other elements give insufficient and fake sense of control. That's what I wanted to insist on, and that can really drastically affect your reserves estimate. So the last thing I may add is thank you for following this presentation. Goodbye, and I hope to see you soon. Thank you.